We're going to go ahead and get started. Today's discussion will be measuring flow in difficult conditions. We're going to go through, I'm going to review some of the basic flow measurement techniques, and then I'm going to talk about some more advanced technologies and techniques with using non-contact laser. This picture right here is the ISCO Flow Lab. We do a lot of design development work on this facility, which really helps us continue to improve our technologies. And so I'll just kind of keep on going. Why are we measuring flow? I&I studies, or flow surveys as they call them in the UK, enforcement, pre-treatment, industrial pre-treatment, billing, water custody transfer, which is a city discharging to another treatment facility. See that in places like Atlanta, Phoenix, Milwaukee, Boston, Denver, and so on. So a lot of places out there do that. These pictures are something you may have seen in the past, which would be one of the older style flow meters, has a built-in printer, has the keypad and display. The one on the right is a flow logger. So these are some of the older ones that we had, and we've since upgraded those. Depending on what your power options are, you have the Signature, which is the more permanent meter. We also have a portable version of Signature, but most commonly when you use a portable, you're probably going to be looking at a 2100 series flow meter. One thing about the Signature is it gives you unmatched flexibility. It's a smart device, which means I can plug and play up to 9 different technologies on the meter itself. So easy to adapt to your application. But before we started with that, we had a lot of these out there that you may have seen, which is a 2150 area velocity flow module. So the area velocity flow module uses a formula which Q is your flow is equal to the area, done using a level measurement, typically pressure or ultrasonic. And the V is your velocity component, which is typically Doppler. We have a couple styles at contact, and today we'll talk more about the non-contact. So let's go and kind of give you a better idea of what something looks like in the flow. You have a sensor, traditional, that's on a ring in the bottom of the pipe. It measures the level using a pressure technique, and then it uses a velocity Doppler signal to measure the speed of the water. Okay, so let's talk about why use a non-contact sensor. Obviously, safety is a big reason. Maintenance is also one. Nobody wants to have to get in there and clean it if you don't have to. So one thing that we do provide is a lot of different technologies for your application. So I think that's one area where we do a pretty good job of giving a lot of options. Today, though, we're going to talk about the laser. And what the laser does is the laser uses a non-contact ultrasonic sensor in the back. It transmits a laser beam into the flow itself, and it actually measures the velocity below the surface of the water. We are the only technology out there that measures subsurface velocity. There are other surface velocity ones, but nobody does it below the surface, which is our patent. So before we talk about the laser, let's talk about our ultrasonic and what we do on that. We put the ultrasonic sensor to measure level in the back of the sensor, and we put it at an angle, which will allow moisture to just run off that sensor itself if it does get submerged or just in the humid environment. We have a built-in deflector plate part of the molded housing, and for that reason, we take into account the dead band, which is typically 12 inches, and now the laser will read all the way up to, including being submerged. We can be 10 feet away from the water, minimum water depth. Okay, so that's how we do the level measurement. Let's talk about the laser. The laser pointer has a fixed focus point. What we do that's different on the laser itself is we actually change the focal point inside the laser itself. We transmit a known frequency like any Doppler device. We measure off the reflected particles or trained air in the water. We know the transmit frequency, we know the return frequency, and we can calculate the speed of the water. So I'll give you another view of what that looks like. This is a front view, side view. And when that laser transmits, the signal coming out is about the size of a quarter. Where it hits the water is a very tight focal point. That's what we need to make sure we have is a very tight focus point. That's known as converging section or point of convergence. What's pretty unique about the laser is it takes 5,000 spectral velocity readings, and it does all that in 2 seconds. So by comparison, a standard area velocity takes roughly 500. So we're doing a lot more in a very short amount of time with the laser. Okay, so one of the things that I like about the laser is the diagnostics. I want to know when I get a reading if it's a good reading or not. And every time it takes that reading, the frequency on the bottom is the speed of the water. The more that agree on the return signal, the bigger and better that signal looks. So this signal right here is telling me we have very good return signal, and we have a lot of agreement on the return frequency. So we're confident in the reading that we're getting. The bottom line there is noise. As the water speed slows down, that peak will actually shift to the left. So what the laser is able to do is read very, very clean water as well as very slow moving water. This is a measurement of the quality of the velocity reading, and it's stored in the memory. It's stored as a value called Doppler Power. We need to see a minimum of 1,000. Okay, so let's talk about some of the certification. We have an MCert Class 2, which is Europe. Our current published spec are 4% of reading. We have third-party test results. One of them is from the Irrigation Training and Research Facility in Cal Poly San Luis Obispo, California. 1.8% was the absolute error calculated by that one. We also have tested at another well-respected lab on the East Coast known as Alden Research Lab, and we were about 2.7% on that one. So very good results from the testing that we've done with the laser. We designed it for some basic collection system applications. So these are kind of the slam dunk easy ones. Large pipe, anything greater than 36 inch. And we're also seeing a lot more small pipes. So these are pretty easy to do, and we have no problems getting readings. What we're finding though is more and more people are trying to measure difficult applications such as high velocity, low level, which are going to be steep pipes, low level raw water velocity, and that's typically less than 1 inch. And most sensors will need 1 inch minimum to be able to read. So we're seeing a lot more lasers going to those types of applications. Slow velocity, less than 0.5 feet per second. Residential collection system, we'll see that a lot. Industrial monitoring as well. We'll see slow clean applications, wastewater treatment. Effluent, we'll see chlorine contact chambers, drinking water, plant influent, stormwater. And stormwater is a challenge because you have a wide fluctuation in flow conditions. You can go from either no flow to just a lot of flow in a short amount of time. Okay, so here's a shot I thought looked pretty good. This is a low-level, high-velocity application up in Minnesota. Their depth here was less than 1 inch, so they couldn't put a standard AV sensor in and get good results. The laser spec is a 1/2 inch for velocity, and we will read up to 15 feet per second. This shot right here gives you an idea of how the laser was installed. The laser can mount either direction. We don't care if it's pointing into the flow or away from the flow. This is some of the data that we got from a test site in Canada. Up here, you'll notice to the right in parentheses would be the average velocity for this time period. So you can see it was 13.26 feet per second. So it's just moving really, really fast in that line, very challenging. Then we have a lot of slow velocity applications. More and more we're seeing those, and this is going to be difficult. Anytime you're below a 1/2 foot per second, you're going to be kind of at the low end of most technologies. Well, why can the laser work? It can because of the good signal to noise ratio. And we can read extremely low, extremely slow velocity. Again, our spec is a 1/2 foot per second. There's a shot right there to kind of show you what a laser looks like in a very slow moving application. We don't need surface ripple to get readings. That's the benefit of the laser. Here's an example of some data where we collected low velocity. That dashed line there is our 1/2 foot per second spec, and you'll notice that we went far below that spec and did a really good job measuring that. That velocity was 0.39 feet per second. So very, very slow, and we can do a good job measuring that. Okay, so what's it look like? And people ask me this all the time, how do we install one of these? So I'm going to give you a couple ideas. This is our flow lab. So we just have notches in the top of that PVC pipe, and it doesn't need to be that big, about 3 or 4 inches wide and about 11 inches long, and the laser can read into that. So that's what it looks like there on the flow lab. Industrial monitoring. This was a really good shot and a real good application if you can monitor this or put a sensor on an application like this, you're going to have really good results. We don't have problems with irregular shaped inverts and things. We got a very nice uniform pipe dimension. So for industrial monitoring, this worked really, really well. We also have one in a shrimp factory in Louisiana. They had to measure this flow, didn't have a great way to do it. They just cut an opening in the top of that PVC and put that laser right in there. This is one that was fairly tight space. This was in Nevada, Henderson, and they're trying to measure that. The ultrasonic level is roughly right below where that handle is, and the velocity obviously is going to be at a 45-degree angle out of the nose of that. So easy to install that. They got pretty creative there and did a really good job. This is a wastewater effluent discharge. You'll notice there on the wall, the way that bracket is mounted, there's just two bolts that hold that bracket to it. The laser has a built-in accelerometer like your cell phone, so it knows its XY axis or the pitch and roll. When you install, you know exactly how you're positioned. Those are key because if you're every degree off of 45 is about a 1% error in velocity. If you're not exactly perfect, or if it goes underwater and then comes back from being submerged, if you're off a degree, it can affect your accuracy. The laser with the built-in accelerometer will take that into account and mathematically correct for it. So easy to install and very, very good way to compensate for it. This is a site. One of my salespeople sent me this video and said, "Rick, will it work here?" And I said, "I don't have a clue. Let's try one out." So went ahead and we installed one. And you'll see here, very turbulent, a lot of entrained air, not an easy application. So they installed a laser, it looks like this. So once we installed it, we started getting some data. Looking at the data, the top pane is level, second one's velocity, third one is flow rate. When I looked at that, the velocity didn't look real hot to me, and it was very, a lot of dropouts in there. So what I did was I downloaded a diagnostic, again, the laser diagnostics. You'll notice there's a very low frequency, low velocity diagnostic or return spectrum. And then we also have a very high return spectrum. Well, that's telling me that we're getting the right reading, but we're locking in on the left. So with some of the advanced capabilities of the laser, we're able to actually avoid that low frequency thing and say, let's look to the right. I don't want to look at that low frequency. When you'll see right here, the line, the red line is where I made the change. The data past that would be after that change was made. So made a tremendous improvement on their data, and they didn't have to go in and do expensive construction, which is the next step. UV disinfection channels, another one of those applications where people want to measure. In the past, they would measure level, but now they want to measure the velocity as well. So UV channels are challenging, very clean, very slow, and the laser did a really good job there. Here's one that was a high velocity rectangular channel, which was a very challenging application. You can see with the turbulence. The nice thing about it was an easy install. They just cut out part of that grating and put the laser right on top. So that worked really well for them. Here's one that was a drop pipe application. So normally we read the level right below it, and we would try to read the velocity into that. Well, what we had to do was something like this, and now we have a ultrasonic that's actually mounted horizontally. It now will read the level inside the pipe, and it will read the velocity in the exact same location. So now we're able to compensate for these types of bad locations. There's a remote ultrasonic as well. This was the influent of a wastewater plant. You can see it kind of drops off into that channel, that box culvert. CSO outfall, this is one that we did in Omaha. The level was only about an inch deep, if even that, until they had big rains. And so it was going to have to be challenging because they were going to read level right below it. And then they would try to focus the laser up under that pipe. So that wasn't going to work till we put the remote ultrasonic in there. And then we were able to read that location as well. Here's one where we see more and more of these types of applications. It's making a bend in that manhole. How do I measure it? Can I measure it? The answer is yes, you can. And what we do on that is we would put a remote ultrasonic, typically in the inlet of the pipe. You could put on the outlet too, it doesn't matter. And in this case, now we're reading velocity and level. We don't care if that pipe's making a turn or not. Okay, so high river or high velocity river applications. You go from low flow to a raging rapid during a storm event. You have sensor cables to deal with inaccuracies due to the velocity measurement in such a big channel. And benefit of the laser flow is it can read slow and low flow, can adapt to those high flow conditions, and you have nothing in the water. It's going to be accurate throughout the entire range. So this application looked like this right here. So you can see that laser off of a bridge. They used a sunshade for the level sensor part of it, but they were able to camouflage that so it wasn't so obvious to the naked eye. This is a large channel installation. This is another one where we get asked, well, how many sensors do I need? Well, if your flow is uniform, you can get by with probably one. If you have non-uniform flow, you might want to put one on each side and just split the channel in half. So this one was another one. This was an irregular shaped channel in California. Normally they just have water in that trough. And this doesn't look, I don't think, is a weir or a flume, but it's some sort of a way to try to control that flow. But what we did with this is we just did level to area data points, and we're able to read the entire flow range from low flow to high flow. Okay, so what happens when we go underwater? Well, this is not a great pleasing picture, but this does happen. So when we look at laser calibration or maintenance, what do we have to do? Well, it's a non-drifting ultrasonic, so periodic check would be good enough for the most part. Velocity verification, we do not require that, but if you wanted to do a manual profile, you certainly can. The advanced diagnostics really tell us what we're looking at. And when I graph Doppler power, and I can see if we had any errors. So you can see in this one, the top one was level, velocity, and flow Doppler power. You'll notice the level went up, the velocity went up, and it sure looks like we went underwater. So at that point, the Doppler power is telling us we're struggling to get a reading, so you might have to go out and figure out what's going on there. You can alarm off of all of this, by the way, with the cell modem. So what we do when we go underwater is we have a level sensor, area velocity sensor, pretty much a standard one. We put it on the bottom of the laser. We read the pressure using levels, so we can read all the way up through the submergence in that manhole. And so it works quite well, actually. It will switch automatically back to the laser once the event's over. So one continuous output, you don't have to switch it in the software. It will do it for you when you program it that way. Stormwater, a lot more stormwater applications where people are using laser. The one on the left was just a fairly simple install using some C-clamps, and the one on and that's what it looks like on the inside of the pipe looking out. We did have a site that I call extreme stormwater. This thing was very clean, very low and slow flow. This happened to be out in Hampton Roads area, and they're doing stormwater monitoring out that, but they wanted to measure that little bit of trickle of flow. So we were able to get the laser dialed in to read that, and it's actually all the way down less than an inch, and the velocity is about a quarter foot per second. So did really, really well. All right. So that's how the laser works and the applications that we use them in. But we now have just released one that's called the LaserFlow EX. It's rated for sewer manhole environments NPS 820. We have more consultants that are specifying Class 1 Division 1. In Europe, it's ATEX Category 1G Zone 0. IECEX rating, international as well. And LaserFlow is the only one that actually meets all of those requirements for the most part and is a non-contact subsurface velocity measurement. So some of the differences between the old laser or the standard laser and the new laser EX. The new laser non-IS unit will be blue. There's really no other changes to the features. It will be compatible with 2160 and the signature flow meter. LaserFlow EX is going to look like this. It's black, it has conductive fibers in it, so it's a little bit different, and the ultrasonic is mounted externally. There's a large label on the side that'll tell you that it's an EX unit. The one thing that is a little bit different due to power restrictions it is limited to 3 points below the surface in the center. So we had to make some changes to that, where the standard laser can do a little bit more profiling. This is known as a multi-point, multi-depth velocity method. Okay, again, what is NFPA Zone 0, Division 1? It's what the customer is looking for out there. They're explosive environments. The standard is going to apply to collection system, combined sewers, storm sewers, pump stations, wastewater treatment plants, sludge handling facilities, chemical handling facilities, as well as treatment works. So where we're seeing this requirement: Canada collection system, Australia, Singapore, UK, Germany, Massachusetts, Boston area, New York City, Phoenix, Milwaukee, Seattle, and the list just keeps growing and growing. So we're very fortunate to have that technology now, so we're able to cover these customers in addition to the ones that were using the non-IS laser. All right, so one thing that we really wanted to make sure was that we did not lose any performance capabilities. So in this case, we have dueling lasers. This is one of the older style lasers with the black housing compared to the Laser EX. So these are head-to-head tests. And what you'll see there is that the level in the top pane is comparing the two, the velocity in the second pane and the flow rate from the third. So it did really, really a good job. We didn't lose any accuracy on the tests that we did. So one thing that we feel like we've accomplished is that LaserFlow is really gaining market share and superior non-contact flow technology. So just been a lot of fun to work with. LaserFlow EX provides complete solution to any customer's non-contact needs. Now they can cover it all the way, getting accurate data with no risk or minimal upfront cost. So very exciting what the laser can read, what the applications are that we could never read before. We're finding, again, more and more people are trying to measure some of these. We also see people now trying to verify their flumes are right. What I've seen, and I've been doing this for quite a number of years, is that just because you have a flume and you have your ISCO handbook, you can see that it read the level right and it did the math correct on the meter. Doesn't necessarily mean that flume is right. So a lot more verification of flumes and primary devices up there. So with that, I'm going to turn it over to some questions. All right. Okay. So appears that laser flow velocity is limited to a defined channel, geometry, pipe, etc. What is your preferred non-contact method for regular channels? Other companies, okay. So what we do is, we're using a level sensor, ultrasonic, and that's how we're getting our level measurement. It's a very accurate way of doing it, but your flow hydraulics or the channel shape would be the one thing to be concerned with. We can do level to area data points on all of our equipment, so we will take into account that. The laser is not going to read the entire width of a channel or a 10-foot wide channel, but it's going to tell you very accurately what it sees, where it's looking. So good question. What is the weight of the laser flow? It's about 12 to 15 pounds. I haven't looked at the weight for a while, but it's not terribly heavy. What is the maximum submergence with the laser? The laser rating is 6 feet for 72 hours. So it'll hold out the water up till that point. The nose piece of the laser is like a diver bell. So it's going to hold the moisture out, and it does a really, really good job. The laser also has a built-in what we call optical clarity system. It will detect backscatter of laser light. So if you had it in the back of your truck in the wintertime in Nebraska and you put it in a 60-degree manhole, it could fog up a little bit for you. Well, what this optical clarity system does is it takes and turns on a small little window heater and just warms up the glass. So that's worked really well. How do you deal with dialing in a laser in a wide range of flow depths? The laser will automatically adjust how deep the focus point is based on the water depth. So when you have very low flow, it won't focus as deep as it does when it goes to a high flow condition. All right, I think, let's see. Okay, with the mounting bracket being held by two bolts, has vibration caused any interference with readings? That's a good question. I would say the answer would be yes. If there's enough vibration where it could vibrate that laser sensor, then you could see some possibly noisy velocity readings. What I would tell you is I have not seen an application yet where that's been an issue. The way the laser takes those readings and as fast as it does it, it would have to be pretty coincidental, I think, to hit it at exactly that time. Let's see. Okay, looks like the performance of use of the meter is great. Most difficult part is going to be installation. As industrial pretreatment, I'm going to be MacGyver and wondering what types of monitoring equipment. Most manholes have step down, maybe something that can mount to those steps. You can get very creative. If you notice that one picture I had that showed the one in Henderson, Nevada, they used our U-channel mounting bracket, but they also used a different unistrut kind of design to mount it into their manhole itself. So yes, you can get very creative. I've used all thread before without even using the stainless steel. Just go get some stainless steel all thread, and like that picture where I showed the UV disinfection channel. That was just a quick test, but that worked really well. All right, Tori, well, I think we ran out of questions for now. Want to thank everyone for attending. We will be doing more and more of these as time goes on, and appreciate the feedback. And feel free to email me if you have any questions. My email address is rick.dey@teledyne, teledyne.com.
Yeah, and if you have any questions, follow up on, you can also send them to me after the webinar, and I can pass those along to Rick and the team to answer. Once again, this is being recorded, so it will be available for your review along with the presentation slides that Rick went through. Those will be available on Teledyne ISCO's website probably early next week. And lastly, I want to say that we're always looking for feedback on our webinars and how to improve things, or if there's different topics that you'd like to see covered. So after you leave the webinar, you'll be prompted to fill out a survey. We appreciate the feedback, so any feedback you want to provide, we welcome it. And I also want to thank Rick for walking through this presentation, and thank everyone for joining us today, and hope you have a great rest of your day.
Thank you.